To understand this video, you need to have watched the previous video on intermolecular forces. Phase changes. Most people have experienced chemical phase changes. We have defined the three common states or phases of matter as solid, liquid, and gas. When a substance moves between one of these stages or phases of matter, it undergoes a phase change. These changes can be defined in terms of their intermolecular forces and the energy of those molecules. Moving from the solid phase into the liquid phase is called melting. And going from a liquid to a solid is called freezing. These terms are commonly used to refer to these processes, even outside of a scientific context. There are many forces that combine to hold a substance in the solid state. However, we will consider the three most important based on things we already know: temperature, pressure, and intermolecular forces. The intermolecular forces between molecules determine how tightly they are held together. However, just like chemical bonds, if we increase the energy or heat of the system, those bonds will start to break. We know that as the temperature increases, so does the kinetic energy of the molecules. If the heat increases the kinetic energy enough, then the molecules have energy to break free from the intermolecular forces holding them together, and they will start to melt. That is, move into the liquid phase. In the liquid phase, some but not all of the intermolecular forces have been overcome by the kinetic energy of the molecules. Imagine 50 people standing in a room holding hands. If they are all standing still, as in a solid, they would all be holding hands. However, as they start to move around the room, they will need to let go of some of the hands they are holding. This is like a liquid. Some are holding hands and some are not. The remaining intermolecular forces create things like viscosity. The higher the pressure, the more energy it takes to get those molecules moving against that extra force. Thus, increases in pressure move substances towards a solid, and decreases in pressure move substances to a gas. But we will discuss some of the details of pressure later. The energy required to break those intermolecular bonds when moving between the liquid and solid phases is called the enthalpy of fusion, or delta H fusion. This has a positive value when it represents heat being taken up to break the intermolecular bonds, and a negative value when it represents the heat being removed to form intermolecular bonds. When H2O melts, it requires 6.01 kilojoules per mole of energy to break some of the intermolecular bonds holding it as a solid. On the flip side, when H2O freezes, it gives off negative 6.01 kilojoules per mole. Melting is an endothermic process, and freezing is an exothermic process. This matches with how we have discussed enthalpy in the past. It is important to note that all substances have different enthalpy values based on the complex interplay of their intermolecular forces, temperature, and pressure. Review the concept of enthalpy in the textbook if you need to refresh. Interestingly, matter can also absorb enough energy to move directly from the solid phase to the gaseous phase. This process happens when you take dry ice, CO2, in the solid form, out of the freezer and it begins to let off CO2 gas. This process is called sublimation, a phase transition directly from solid to gas. The opposite is called deposition and can be seen when frost forms. In the same way that we can talk about the enthalpy of melting, we can also talk about the enthalpy of sublimation and deposition. CO2 absorbs 26.1 kilojoules per mole of heat when it sublimes, and it releases negative 26.1 kilojoules per mole of heat when it is deposited. Finally, matter can undergo a phase change from liquid to gas, like in the case of boiling water. This is called vaporization, and the opposite is called condensation. This also involves the absorption or release of heat, as in previous examples. Here is a diagram that summarizes the different phase changes that are possible and the energy that each requires. This diagram shows changes in the temperature of an amount of water relative to the amount of heat added. The relationship between heat gain or loss and the resulting temperature change is the familiar equation. The heat absorbed or released is equal to the mass times the specific heat times the change in temperature. This should be familiar to you. If it isn't, please review the textbook section on thermochemistry. Notice that the curve is flat during the phase transition. This is because all energy added is being used to break the intermolecular bonds and induce the phase change. So none of it is going towards the temperature increase. Remember that the heat needed to induce a phase change is extrinsic, which means that it depends on the amount, or moles, of a substance. The equation for this value is the number of moles of a substance times the heat of the state change. For vaporization, we would use the heat of vaporization times the moles of substance to get the amount of heat that is used to change state. Let's calculate how much heat is needed to heat 10 grams of solid ice at -4 degrees Celsius to steam at 122 degrees Celsius. To do this, we need to know the specific heat of H2O in its different phases, as well as the temperature at which a phase change will happen. And the heats of fusion and vaporization. We will need to add the amount of heat required to raise the temperature, as well as the heat needed to induce a phase change. We will assume that all this happens at constant atmospheric pressure. We can visualize the final equation for this calculation by simply summing up all the heats of different parts of the graph. From -4 degrees to 0 degrees, we use the change of temperature equation. We need to use the specific heat appropriate for the phase of matter. So for a solid here, we get 83.7 joules of heat to get to melting temperature. Then, we can calculate the amount of heat needed to melt the solid into a liquid. We do this with the moles of H2O and the heat of fusion. For water, which is 6.01 kilojoules per mole, we get 3,330 joules. Next, we calculate the amount of heat needed to heat the liquid up to the vaporization point, which happens at 100 degrees Celsius. We need to use the specific heat of liquid water, which is 4.184 joules per gram degrees Celsius. Next, we need to calculate the amount of heat needed to vaporize all the liquid using the heat of vaporization for water, which is 40.7 kilojoules per mole. And lastly, we need the amount of heat that is required to increase the temperature of the gas from 100 degrees Celsius to 122 degrees Celsius. We need to make sure that all the heat values are in the same units, in this case joules. We can sum up all these heat values to get the total heat that we would need. In this case, 30,600 joules to raise water from -4 degrees Celsius to 122 degrees Celsius. Review and work through pages 20 through 25 in your workbook. Let's consider what happens when we allow the pressure to change as well as the temperature. The lower the pressure, the less heat it takes to break the intermolecular bonds. However, even at high pressures, we can add enough heat to still overcome these bonds. For a particular substance, we can construct a graph. Here is a phase diagram for an unknown substance. In this diagram, The yellow area represents the substance in a gaseous state. The seafoam green area represents the substance in a solid state. And the blue area represents a liquid state. So at 0.5 atmospheres of pressure and 100 Kelvin, this substance is a solid. However, at 350 Kelvin and 0.5 atmospheres of pressure, this substance is a gas. These states are a result of how much energy is needed to break intermolecular bonds at a particular pressure. Triple point represents the substance in equilibrium between all three states. And at the critical point is where the supercritical fluid forms. A supercritical fluid is much like an intermediate phase between a gas and a liquid. It will fill the container like a gas, but it is much denser than a normal gas would be, similar to a liquid. Above the critical point temperature, no amount of pressure can push the substance back into a liquid phase. Again, these points are different for each substance and determined by the intermolecular forces at work. Review and work through the pages 18 and 19 in your workbook.